Hi everyone, this is going to be your post-lab report for your experiment 7, which is the preparation of aspirin. Okay, so the post-lab calculations are very easy, and which you also have done so many times this kind of calculations. So we are given the mass of the salicylic acid used. So if you watch your virtual lab, you know the amount of salicylic acid used 2.121, acetic anhydride 5 milliliters. So those are our reactants, and our product is aspirin. So you can look up the equation, which is salicylic acid and acetic anhydride together make aspirin. So between salicylic acid and acetic anhydride, which one is the limiting reactant? Limiting reactant is going to be the salicylic acid because we use acetic anhydride in excess. So salicylic acid is the one that's going to be limiting reactant. Okay. And then at the end we obtain 1.92. So you were supposed to calculate the theoretical yield and then the percent yield. You guys know how to calculate the theoretical yield based on the limiting reactant of the starting material. So how do you do that? Since we identify this as the limiting reactant because we use 5 milliliters acetic anhydride, and also at the end we add 2 milliliters of water to get rid of any excess acetic anhydride, to break it down to acetic acid and to evaporate it. So that tells us we have used excess of acetic anhydride, but our limiting reactant is salicylic acid. So with the given amount 2.121, how would we find out the theoretical yield? So you guys know how to do this one. In fact, 2.121 is our starting material. So you start with 2.121 grams of your salicylic acid. 2.121, that's correct. And then always we want to make sure that you convert grams to moles using the molar mass of salicylic acid. 1 mole salicylic acid is the molar mass of salicylic acid, which you guys need to calculate. Okay, salicylic acid structure is given in your experiment handout. Also, I believe you calculated this in your pre-lab assignment too. So the molar mass, right? And then the ratio is 1 mole of salicylic acid gives you 1 mole of aspirin. 1 mole salicylic acid gives you 1 mole of aspirin. Okay, that's the molar ratio. And then in order to calculate the theoretical yield, which is in grams, 1 mole aspirin is the molar mass of aspirin. Molar mass, which again you have to calculate it. Molar mass of aspirin, you know the structure and the molecular formula, so you put it in here. So this one you need to calculate. Molar mass of salicylic acid you need to calculate. Molar ratios are the same, 1 to 1, and then you will get the theoretical yield of aspirin in grams, the amount of aspirin that you make with 2.121 grams of starting material. That amount you're going to be putting in this space provided, which is going to be theoretical yield, which is how you're going to calculate. And then the percent yield is going to be, you take percent yield is going to be 1.92 grams, and you divide by your answer to theoretical yield, you put that over here, times 100 will give you the percent yield. Okay, you do that calculation, and then the melting point is given to you, and we also did some solubility properties, and then based on the solubility properties, underline those characteristics listed. I'm going to erase this. Okay, so let's look at the solubility. So you need to figure out whether it is going to be soluble in organic solvent, inorganic, aliphatic, aromatic, polar, non-polar, hydrogen bonding, non-hydrogen bonding. So the salicylic acid is, insoluble in toluene. Toluene is this molecule right here. You don't need to know the structure, but I'll go ahead and show it to you. Toluene is this. This is a benzene ring, so toluene is this. So when you have this ring, we call it as an aromatic group. So it is insoluble in toluene, meaning it is, if you want to find out a suitable solvent, then aromatic is not good, right? Underline those characteristics listed which would be likely to be present in a good solvent for aspirin. So aromatic is a not good one. And then the hexane. Hexane is when you have 6 carbons like that, and then the rest are all hydrogen. So this is, again, this is called aliphatic. Aliphatic, since it does not have a benzene ring, they are aliphatic, and this is aromatic. Okay, and then hexane is non-polar. Also in your handout you will see the characteristic. The toluene is non-polar aromatic, hexane non-polar aliphatic. Okay, so it's not going to be soluble in hexane either. So non-polar we can omit. And then the ethyl acetate. Ethyl acetate is this molecule. Ethyl acetate is given as aliphatic ester. It is this CH3 COO CH2 CH3. Now, do you see this ring in this molecule? No. If it is there, that is aromatic. So this is aliphatic. Aliphatic, and it is an ester. Okay, so that can be considered as polar also, because it has carbon oxygen bonds that will make it polar. But the carbon hydrogen bonds are non-polar. So this is aliphatic, and I would say it's polar. Okay, and then we have ethyl alcohol. Ethyl alcohol is this CH3 CH2 OH, and this is again aliphatic and polar. It is soluble. So this is aliphatic polar, ethyl acetate, ethyl alcohol, aliphatic and polar. And also it can have hydrogen bonding. Acetone. Acetone is this molecule, CH3, CO, CH3. You sometimes see this in your lab that we used to clean up our glassware also. Acetone, it's a polar molecule. It doesn't have hydrogen bonding. Acetone, it's a polar aliphatic non-hydrogen bonding. That is also soluble in that. And then the water insoluble. So based on those things, what do you think would be the good characteristic? And all of these are organic, and water is inorganic, since it's insoluble in water, and all of these solvents are organic except water. Water is inorganic. So it's organic would be a good one. And then between aliphatic and aromatic, which one would you prefer? Aliphatic or aromatic? It isn't soluble in toluene, meaning it's not a good, aromatic is not a good solvent, right? So aliphatic would be a good one. And between polar and non-polar, hexane is non-polar, it was insoluble, but ethyl acetate, acetone, ethanol, they are all polar, so polar would be a good choice too. Hydrogen bonding, non-hydrogen bonding. Let's look at the structure of aspirin. Aspirin has alcohol OH group. So it's soluble in acetone. Acetone is non-hydrogen bonding, and ethyl alcohol can form hydrogen bonding. It would be a good one to have hydrogen bonding too. since alcohol can have hydrogen bonding due to this OH group, since it's soluble in acetone, 9 hydrogen bonding also I would say suitable. Acetone and hydrogen, no, I'll wait for the hydrogen bonding, I'll choose that. Okay, so we can choose these 4 properties for a suitable solvent. Okay then, it's an easy one. That's about your post lab 4 experiment 7 aspirin. Okay then, bye for now.